joint work with Patrick Kennedy Hunt and Kasim Shafi. And so one of the main themes of my talk is to count curves in C star squared. So C star squared is of course a non-compact target. So curve inside it will also be non-compact. So the curve is just finitely many points away from being compact itself. I'm going to formalize a parametrized curve in C star squared in the following way. So it's going to be a smooth projective marked curve like this. So let's say minus G, smooth projective marked curve. And for me, in comparison to the previous talk, I'll always be working with a connected theory, so connected curve G. And together with the map from the complement of the marked points, C star squared, F, and the data that will formalize the parameterized curve in C star squared for me. And of course, C star squared has two projections to C star. We can compose those two projections with the map F. We get two rational functions on the curve C. Then we can ask ourselves what is the order of vanishing at the marked points, x1 to xl. So from these two rational functions, I'll get two vectors A and B, integer vectors. And they'll of course be zero-sum vectors. And I'll write, during this talk, I'll write A over B for the obvious 2x matrix. Okay. Now, what I'll do is I'll consider a moduli space with such objects. For that, I'll first, so for now, I'll fix such a matrix with two such zero-sum vectors. I'll consider the moduli space of these objects. So I'll call this the following way: MG following way, and as usual in enumerative geometry. So I said I want to count curves, so I want to extract somehow numbers out of this moduli space. The usual way we do this in enumerative geometry is to try to integrate over that moduli space. But there's an issue here because this moduli space is not proper. So I need some type of compactification. Before I tell you what that compactification is, I'm going to reinterpret this moduli space in a different way. So I'm going to try to get rid of this non-compact target here. So what I'm going to do is I'm going to choose some smooth toric compactification of C star squared, and we'll write that as x of sigma. So sigma is the fan of the toric compactification I choose. And I'm going to interpret this moduli space as a moduli space that maps to this toric compactification. How do I do that? So this moduli space, it parameterizes maps from non-compact curves to C star squared. And then I'm going to reinterpret that as a map from the full curve to the toric compactification, where, so here, at the markings, we have zero pole data given by this matrix, and here this matrix is going to be interpreted as tangency data. So these marked points are going to be mapped to the complement of the dense torus in this toric compactification. So these marked points get mapped to the toric boundary, and the matrix AB is telling us some type of tangency information with the boundary. And okay, I do now write down an example, which maybe will help clear this up a bit. So take our matrix A, B, be the following. Take our matrix A is form, and I choose my toric compactification to be the following. So it's going to be a blow up of P1 cross P1 P1 torus 6 point, and I will name these column vectors here P1, 2, 3, and 4. And we can draw these vectors in my fan. So P1 is P1. And of course, V3 is the 0 vectors, which is the origin here. V4 is here. Now I can draw how does an element in here look like. So it's going to be a marked smooth projective curve with 4 markings. Full compact curve to my target. My target is this toric surface. Then I'll draw the image of the curve under this map. So that's going to look like this. Yeah, so for the first marking, I look at the first column vector. I see the first column vector is along this ray. That's telling me that, this marking is being sent to this the corresponding divisor. So this is the network X1. Similarly for X2, X3, X4, they get mapped here. You see X4 is the column vector is 0, 0. That is, and 0, 0 is here. Being mapped to the 0 cone. That's telling me it's being mapped into the interior of the torus. So that could be somewhere here. Yeah. And furthermore, these for each column vector, if I look at what multiple that column vector is of the primitive direction, that gives me the tangency order. So in this case, it's just 2, 2, 2, and the contact order 0 here. So that's the picture of how I'm reinterpreting my moduli space. Other questions here?
You don't really need the toric variety, the toric surface to be compact here, right? You really need the rays only to divide.
Yes. So yeah, for my later problem, when I compactify the whole moduli space, I do need.
So later you'll need it.
Yeah, and you made a good observation. So for this talk, I'll always choose my toric surface. I'll always choose the fan in a way such that these column vectors are also rays of the fan. I can always do that. Right? Yeah, that makes sure. In other cases, that it might happen that the curve hits like a codimension 2 star. I mean, like small, higher codimension than just devices. But I mean, you can always choose to do that.
Is there any reason why you chose the fan to be finer than the stuff spanned by the red rays, or is this just arbitrary?
I chose it so just to show that I don't have to, I don't have to just choose those rays.
Okay, so you have
Yeah.
the freedom to make it finer than the
Yeah.
rays. Okay.
Okay. So, okay, then, yeah, so what have I done? So I've vaguely told you, I've reinterpreted our moduli space of maps to non-compact thing as a moduli space of maps from compact curves to a compact target with where we have some prescribed tangency data with the toric boundary divisors. Compactifying this moduli problem is exactly the topic of logarithmic Gromov-Witten theory. So log geometry, logarithmic geometry gives us a compactification. This is called the so-called moduli space of stable logarithmic maps to my target X sigma. This is a construction due to Abramovich 10. Receiver. Yeah, so okay, so compactification. I told you it's a moduli space. I'm not gonna quite tell you exactly what this moduli space parameterizes, but I still want to give you some feel for it. So if I take a stable logarithmic map in here. So what is this? My stable logarithmic map. So it comes associated with the stable logarithmic map, basically is two pieces of data. So two pieces of data. So there is still a map from a marked curve to my target. So but now the curve is possibly nodal. Maybe connecting with the previous talk, this map, the underlying, there's an actual stable map there, so an element of the usual ordinary Gromov-Witten theory moduli space. So you have the underlying stable map. And so this should be thought of as algebraic information, but associated to a stable logarithmic map, there's also tropical information or something tropical, combinatorial information. What is it? So it's going to be a piecewise linear map from a tropical curve to R2. And so this tropical curve is going to be the dual graph of the underlying source curve of the stable map, with where the edges are given some type of metrization. So the edges have edge lengths in some sense. So suitably metrized graph, suitably metrized dual graph of this curve. And okay, there's not exactly telling you how it's metrized, but there's the tropical information and the algebraic information have to be compatible in some sense. And okay, I want to give you some feel for, I mean, I said I compactify the space. I want to tell you maybe what a map of the interior looks like. So, of course, if I take F in the interior space, of course, the algebraic information should be clear because that's there's that map. And but maybe what's interesting, what is the tropical map? How does that look like? So the associated phi. So the tropical map is somehow trivial. So the tropical curve is just one vertex with unbounded legs coming out of it. And there are as many unbounded legs as there are column vectors in this matrix. And this. And the map is two. The map sends the vertex to 0. So 0. And each unbounded leg is sent to the ray spanned by the associated column vector. And okay, you see now that for an element in the interior, somehow the tropical information is very simple. And you know the main theorem that I'll be stating later is going to be something called a tropical correspondence theorem. And one of the philosophy of that theorem is to trade algebraic complexity against tropical complexity. So somehow in the interior of the moduli space, your algebraic complexity is somehow big and tropical complexity is somehow small. And the idea of the tropical correspondence theorem is to go deep into the boundary of the moduli space of stable logarithmic maps, where somehow the algebraic complexity will be very small and the tropical complexity very as maximal as possible. Yeah.
Is this uncompactified space, is it dense open or is it just some main component?
Yeah. So I say compactification in a very loose sense. So you're of course right. It's not in general, this thing is not going to be a dense open. This thing can have multiple components. It'll be an open in a main component.
Okay.
Yeah. So okay. Hope I give some feel for this space. Then I'll write down the fact I'll use about it. So of course, as I mentioned, if the moduli space is proper, and of course I need some, so to be able to integrate against the moduli space, I need some kind of fundamental class. And of course, these space, like I said, these spaces are kind of very singular. They have multiple components of different dimensions. So it's not a priori, it's not so clear what a fundamental class should be, but there's some large abstract machinery by Bernd and Fantecchi and the original Ross-Seibert paper tells us that there is a fundamental class of a fixed degree that is the right fundamental class in a sense. So the virtual fundamental class in this way, and it lives in homological, so I will write as a homology class in this degree. Homology of X moduli space, and it's with Q coefficients. Okay, so from now on, I will specialize my matrix AB is going to be a following form. Here, non-zero column vectors, m of them. And 0 vectors. Yeah, so Now I want to define some numbers, so to define the numbers, I first need evaluation maps. Or let's say so stable logarithmic maps. Remember, an element of its space did still parameterize actual stable map. So map from the marked curve to my target. And what I can do is I can evaluate at a marked point to get evaluation maps. Evaluation maps. Target. Sigma. And then now I can define after my invariance. The first logarithm invariant I'm going to define is the following. We integrate against virtual class. What are we going to integrate? For the point class field, so when I say, so using these evaluation maps, I can pull back homology classes from the target, and I'm going to pull back point class. By point class, I just mean the point residual of the homology class corresponding to the point. Pull that back, intersect with the virtual class, I get some numbers. And of course, if I want this invariant to not be zero for stupid reasons, I definitely need the homological degree of the insertion and the virtual dimension to coincide. So this constraint tells me that the genus has to be exactly n minus n plus 1. And if the G is in exactly this correct genus, I call this invariant with NAV. Okay, let's do mark. So my first remark, so for my remark is going to be saying that these numbers are intrinsic to C star squared. What do I mean by that? You remember I chose some smooth toric compactification of my C star squared to define these numbers. And what I mean by intrinsic to C star squared is that these numbers do not depend on that choice. If I chose any other smooth toric compactification, you will get the same number. So this is the result of a Brown-Witch class on the birational invariance of local invariance. Questions? Example. Yeah, so example is okay. In this case, already being considered, then I claim the number NAV. 12. And 12 is exactly the number of rational plane cubics that go through 8 points in general position. And why is this is not a coincidence? So if I choose my compactifying toric variety sigma to be PQ, then let's draw the toric variety. Like this. then you can imagine if I draw a generic plane cubic, that will look like this. So we have to have a node. You see a generic plane cubic will intersect each boundary divisor of P2 exactly 3 points. And it affects it in transverse ways with contact order 1. And we see this is exactly coincides with this contact data, right? 1, 0, 1, 0 here 3 times hitting this divisor with contact order 1, and similarly here and here. So it shouldn't be too surprising that this number actually coincides with the number of cubics. Of course, it's not a proof, but to give you some.
Is there not a 3 factorial cube missing?
Yeah, I think this is something that in a few papers is kind of wrong. Yeah, I think there might be a factor, there might be a combinatorial factor missing, depending on if you. Yeah, so with this relative invariance, some people built it in, and I'm not sure. So you might be right. There might be a combinatorial factor. Yeah.
So why is that? Is the issue like whether we label the mark points or not?
Yeah. My co-author actually mentioned this to me, and in another paper we relied on. Yeah, there's this combinatorial factor, I think. Yeah, it's missing in a lot of papers. So yeah, I thought I would just say more or less it's 12, maybe. Yeah, because I know some other people also build when they define a relative from a Whitney invariant, like Kunko Pandripand, I think they automatically divide by the automorphism group of the partition. So that's probably so okay. Yeah, so
Can you say once more what the 8-0 columns do?
yeah, so the 8-0 columns are contact order 0 points, and for those I want to say that they are markings that generically will map into the interior of the toric, right, into the dense torus. And for those are the markings where I impose the point condition. Then actually race. Now, what I also have is I have stabilization. So an element of my moduli space, like I said before, it also includes a map from a curve, my target. What I can do is I can forget the map, and I just have the nodal curve. I can stabilize it, so I get a stable curve. From this moduli space, I have a stabilization morphism. So MGM plus M bar. Of course, there are all kinds of interesting cohomology classes on this moduli space, of which the psi classes we saw in the previous talk. And I can use the stabilization model to pull them back and then intersect with the virtual class and get even more interesting numbers than the numbers I've defined there. So I'm going to fix a vector of non-negative integers, A1 to Kn. And I'll require numbers should satisfy the following equation. This equation will be clear in a minute. So, okay, what am I going to do? I'm going to define for every genus greater than or equal to 0, I'm going to define an invariant. For every genus greater than or equal to 0, as you can see, I've added some interesting classes. So there you can see the psi classes, which only appeared in the previous talk. They are churn class. They're the first churn classes of some natural line bundles on the moduli space of stable curves. And okay, I've pulled back these classes here, stabilization morphism, to my moduli space, and I've just sort of suppressed that from the notation. And there's lambda G. So there's a natural bundle on the moduli space of stable curves called the Hodge bundle, the rank G bundle, and I take its top churn class, and that is my lambda G. Okay. Now, okay, I should give some intuition on why consider this invariant. So let's first set G equals 0. When we set G equals 0, then this we just get a 1 here. So we can ignore this. And we have the genus 0 moduli set. Then we look at again, we want the insertion, the degree of the insertion to match the degree virtual dimension. And you'll see that that constraint is exactly this equation. And then what do? I start increasing genus. So let's increase the genus from genus 0 to genus G. Then what happens is that the virtual dimension, that will increase by G. And this is something very specific. This is something very special, special property of Gromov-Witten theory of surfaces. Yeah, and then to make up that increase in virtual dimension, I input this lambda G insertion. So yeah, that makes up for it. Okay. Yeah, so that is one that gives you some feel for, okay, it's a reasonable thing to do. But another perspective is that actually these invariants that I've written down here are actually invariants of a threefold. So it's an invariance of the threefold x of sigma cross A1. Of course, the one direction is non-compact. So if you look at a curve inside here, it'll always be contained in the fiber of the projection to A1. So And if I were to projection to A1, that's just a copy of x of sigma. So somehow counting curves on this, so integrate integrals against the modular space of stable logarithmic maps. This target should be, one should be able to relate them, the modular space of stable logarithmic maps, to this target, x of sigma. And the correction factor that appears when you go from the theory of x of sigma cross A1 to x of sigma is exactly the G Chern class of the dual of the Hodge bundle. This is exactly this factor here. So that follows from the virtual localization in the A1 direction. These are actually invariants of a threefold. Yeah. Questions?
Are you pointing this out because you're gonna form the toric variety then, right? Or
I'm pointing that out. It'll be maybe clearer when I write down the name here.
Yes.
Yeah.
So usually when you localize it, I mean, you have this torus action on this toric target, and then you can localize with respect to this action.
Yeah.
But in this log case, does this toric action affect the tropical data too? Like, does this torus act on the tropical data at all, or does it?
Yeah. I mean,
Oh, it does. Okay.
Yeah, the tropic, the C star squared action tropicalizes to the R2 translation on the command. Right.
Okay.
Yeah.
I
So-
see. Okay,
Yeah.
I understand.
I
Okay.
should say that, this is one of these things that is not really accessible to us yet in logarithmic Rom-Witten theory. The torus localization formula does not really exist yet.
Ah.
Yeah, so I mean, I think Tom Graber is working on it. Yeah, I don't know what the state of that is. So. Will be the main theorem of the talk. The joint the theorem is with Kennedy Hunt and Patrick Duffy. Oh, I know this. Right, the first. So, okay, so this theorem is going to be a tropical correspondence theorem. So it's going to relate something algebraic, algebra geometric, with something tropical. I'm going to write down the algebraic thing first. The algebraic thing is going to be a generating function in these invariants that I just defined there. So the formal power series in these invariants and use a formal variable. The algebraic side, this is equal to the tropical side. It's going to be a sum over tropical curves. That's from abstract tropical curves to R2. And I'm going to write a bunch of properties of these tropical curves that I will count. In the first initial way out that I write, it might not be very clear, but I hope an example later will clear up these properties. So first, I'm going to count genus 0 curve tropical curves on the right hand side. And some properties. So F, the tropical curve has a degree given by the matrix AB. What this roughly means is that the tropical curve has degree AB, is telling me that the unbounded legs of the tropical curve point in the direction of the given by these column vectors in this matrix. Okay, for the theorem, statement of the theorem, I fix a bunch of point conditions in R2. P1 to Pn are going to be elements in R2 to the n, chosen in some very generic way. I will not explain, but spread out nicely, some random fashion. And then, so my point conditions, my tropical curves has to pass through those point conditions. Now, the more interesting part is that F. So now the powers of the psi class come into play. So F has, so at a marked point, we require some valency of the tropical curve. So F has valency Ki plus 2 at the point Pi. I plus 1. Okay. Counting tropical curves in R2 passing through points with some valency requirements given by the vector K, and each such tropical curve a count with some multiplicity. The multiplicity is going to be a product over the vertices of the tropical curve. Each and will be a Q. So this is going to be a Laurent polynomial. Yeah, Q plus EQ to the 1/2. And okay, later I'll show you some explicit formulas for this. Yeah. Okay. And it really only depends, these multiplicities really only depend on what is locally happening around that vertex in the tropical curve. Okay. Yeah, okay, now you might see that I've given you the left-hand side is a formal power series in U, the right-hand side is a Laurent polynomial in Q. I have to tell you how to go from Q to U. That is given by this transformation Q equals 3IU. Yeah, and yeah, the reason why I said before that it might become more clear why I'm saying this thing about threefolds is this transformation Q equals EIU. It's something that appears in the so-called Gromov-Witten BT correspondence. So in that correspondence, some and that correspondence is really about threefolds. So some generating series of Gromov-Witten invariants of a threefold is equal to a generating series of BT invariants if you do the Q equals EIU transformation. And that is the reason why I mentioned this thing here. So this actually is invariance of a threefold. So that's why, I mean, vaguely, that is why this Q equals EIU transformation is right up here.
So just one question for clarification. When you say that F passes through the points PI,
Yeah.
does that mean that there's a lag in like a lag in the gamma for each of the PI that is supposed to contract on the
yes,
point?
exactly.
Okay.
Yeah.
So is the proof also using the threefold perspective? Or?
No. All the calculations are happening on the.
Okay. Yeah. So this is really sort of, this would sort of also give some correspondence on the threefold.
Yeah. You can ignore this lambda G and write X of sigma cross A1, or you could also write X of sigma cross P1,
Yeah.
but somehow in the P1 direction, you're degree 0.
Yeah.
And here with the point classes, you have to be a bit more careful what exactly you put in here, but more or less in that.
Okay.
Okay. Now, example. So let's do the example. Matrix AB given by following. And the K matrix, the K vector is 0, 1. So we have the 2 point conditions, and the second point condition has a psi class attached to it. Okay. So now I want to calculate the right hand side of our theorem. So I have to count genus 0 tropical curves that have unbounded legs. The behavior is given by this matrix. How does that look like? So first I said I have to choose some point conditions. So let's draw some random point conditions in the plane. Here. Then it's given by this matrix. Like the 1, 0, so something like maybe something that will go like this. And to have something that comes from down here, given by -1. So there's -1, 0, -0, -1. And I know, okay, tropical curve has to be balanced. So what comes out has to, I want it to land here. So I hope more or less place here. So keeping it. And okay, then there's a requirement. The second point condition has to have a psi class attached to it. So it requires valency 1 + 2, so valency 3. That's telling me I have to, when I get here, I have to be like this. And like you said, yeah, technically there are these contracted legs. So I'm drawing the image of the tropical curve. But there are these contracted legs corresponding to these compact order 0 things. Okay. So the right hand side in this case, this very simple case, consists of just one tropical curve. Just one tropical curve. I want to tell you what the multiplicity is. Multiplicity, the product over vertices. So we have this vertex. So this is the trivalent vertex without a point condition on it. So this will be called the so-called unpointed trivalent vertex. It will have the following contribution. Times the second vertex is a bit more interesting because it has psi class attached to it. That will be 1.5. This product, and you can see that if I do the transformation Q equals CIU, you can kind of see here we will get a sine of U, and here a cosine of U. You multiply that out, and then extracting the coefficients of the U, you can get these numbers. Yeah.
So the MFV of Q, are these just these what is it, Bloch-Götzsche?
Yes, exactly. So yeah. So okay. Yeah. So if I set K equals 0, so no psi class conditions, then for K equals 0, we recover a result of K equals so. So he proved this result, and yeah, you met in the case where it's K equals 0, this right hand side will just be will not have these higher valent vertices. It will just be trivalent tropical curves, and the multiplicities that appear will be exactly of this form always, and these are the Bloch-Götzsche multiplicities, and Florian Bloch and Lothar Götzsche, they defined this so-called refined tropical curve count before Kelly proved his theorem. So at the time they defined these refined tropical curve counts, and it was somehow mysterious as to what their meaning is, because you can also see here an interesting thing to observe is that this left, so this right hand side depended on this point conditions, right? And it happens that if I move these point conditions around, the shape of the tropical curves and the number of them can drastically change. But this theorem is left hand side does not depend on this point condition. So it's saying that that it doesn't depend that this Bloch-Götzsche invariant is independent of how you choose the point conditions. And they observed that, and it was and they had their intuitions as to why it is interesting in algebraic geometry, but Bousseau came and gave it a geometric interpretation as to why their deformation invariant, because it actually calculates a log Gromov-Witten invariant. And then
But did Bloch and Götzsche have the psi class contribution?
No, that's exactly the thing. So Bloch-Götzsche did not have. So Bousseau explains the Bloch-Götzsche multiplicity, connects it to Gromov-Witten theory, and then our theorem. So in our case, we are counting genus zero tropical curves with psi class conditions, and for that there's a paper by Blechmann and Schustin. So they wrote a paper on refining the count of tropical curves with high valency conditions. They wrote down a multiplicity, and we get that same multiplicity, but from the Gromov-Witten side. So give their multiplicity a log Gromov-Witten interpretation.
So they define these MFVs and the sum on the right side, or
they that's a purely tropical paper. They write down a refined tropical curve count like this.
all right, okay.
And their theorem is that it is really invariant under moving points around, which is kind of a strong constraint that you can just move points and you get the same number.
Yeah.
But and our calculations give us exactly those multiplicities.
Can you just say a word of like what goes into this explicit formulas? Very quickly. Like, is it technical?
I was gonna have a good time to show it quickly. That would quickly show the formula.
Yeah, no. This takes a little while.
Yeah. So, I mean, first I just this first multiplicity is this unpointed trivalent vertex, which was already there in block and Goethe. Because you have a trivalent vertex, and you have these weight vectors point along the outcoming edges of that vertex. The contribution is this minus I times, q to the so V1 by V2 means so I choose two of the three vectors and take the determinant and the absolute value of them. And that's independent of which two vectors I choose at a balanced vertex. That's this contribution. This was block and Goethe. Now, the more interesting thing is if you have such a higher valent S-valent vertex, with sort of psi class condition, the formula looks like this.
Block and Goethe, was the I there? Or?
So I'm lying a bit. So of course, in their formulas, they also have like a denominator.
Right.
Yeah, and the I is not there.
Okay, but multiplying everything by I.
Yeah.
Oh wait, it's the number of vertices per side. Yeah.
Yeah. And as you can see, this would be the multiplicity I get for high valent vertex. You see, it's I don't know how well visible it is. Oh yeah, that's good. Like that. So it's a sum over symmetric, so over the symmetric overall permutations and choices of permitting those vectors. But okay, this is actually not. So this is how it comes out of the machinery we use to calculate these invariants. But the Blechmann-Schuster multiplicity is a recursive multiplicity, and the way that one works is more or less what you use if you have a high valent vertex. You sum over all choices of two of them, and you pull them out, and what you'll get is a trivalent thing plus something smaller valent. And the trivalent thing has the multiplicity just q1/2 plus q minus 1/2 times 1/2, and then you recursively do the recursion. And yeah, so very complicated. But it turns out you can show, and here we actually needed help. So Thomas Blom then told us this, that he showed us a proof that showed that the Blechmann-Schuster recursion actually matches the multiplicity we compute using local multiplicity. That's what I wanted to show here. Okay, then I'll just very quickly say something about proof. So there is some let's say by now more or less standard log Gromov-Witten theory machinery that will reduce this theorem to calculating its vertex contribution. So at each vertex, you reduce to calculating some generating series, some log Gromov-Witten events attached to a vertex. That will follow from some type of so you torically degenerate your surface, and then you apply something like the degeneration formula in logarithmic Gromov-Witten theory, and some extra work, and basically you reduce to calculating some invariance at a vertex. So you have to calculate these vertex contributions. And to calculate these vertex contributions, what is important is to connect these log Gromov-Witten invariants with something called higher double ramification cycles. or DR cycles. So, I mean, this is, yeah, this is the result that makes this, that facilitates this connection is the result of roofs, Ranganathan. So then once you have DR cycles, a higher DR cycle, we use the property of the lambda G class, lambda G vanishes outside compact type. So I should say these higher DR cycles. So I turn an intersection on the moduli stack of stable maps, log stable maps, into an intersection against the higher DR cycle, which is a certain natural cycle that lives on the moduli space of stable curves. And there I have my lambda G. I use the fact that the lambda G vanishes outside the compact type locus. Then
Compact type, you mean genus 0?
So tropical, so
Yeah.
combinatorial genes, yeah. So the dual graph does not have any loops. That's the compact type locus, and that has the effect. So that was already actually that is a bit used in the simplification here, right? You see here that tropical curves that appear have genus 0. So there already some lambda G did some stuff, but here the lambda G does again some stuff and will cause the DR cycles to split into a product of DRs. And then we reduce to integrals of the form lambda G psi class power of psi class to DR cycles, and those integrals are exactly calculated in a paper of Alexander Buryak and Paolo Rossi. So they have a paper that calculates these integrals. They use some type of there's some type of recursive way of decreasing the psi class power. Their paper is phrased in this language of integrable systems, but in this case, it actually gives you an explicit formula, and when you do Q equals you get exactly that formula that I showed you. I think that's enough.